In this example, I need to verify the identity, the secant of x plus the tangent of x, all divided by the sine of x, equals the cosecant of x divided by the secant of x minus the tangent of x. When we work on identities, we always want to start on the more complicated of the two sides. But in this case, if you look at the left-hand side and the right-hand side, they both look about equally complicated. So I'm just going to pick to start on the left-hand side. Before we start working on the left-hand side, I want to point out a very important clue in this problem. If you look at the binomial in the numerator on the left-hand side, and the binomial in the denominator on the right-hand side, they are conjugates of each other. This means the first terms are the same, the last terms are the same, and they have opposite signs between them. And the reason this is useful is if you take two conjugates and multiply them together, you get the difference of two squares. So in this problem, I'm going to multiply numerator and denominator by the conjugate of this binomial. So I'm going to multiply by secant x minus tangent x. And since I multiplied the numerator by it, I must multiply the denominator by the exact same thing. And now, if you notice, something nice happens. This denominator is the exact denominator I need in my answer. So now what we're going to have to do is we're going to have to simplify the numerator. I know I should get the difference of two squares, but let's just prove it by folding it out. So first terms, secant x times secant x is secant squared x. Outer, secant x times negative tangent x is negative secant x tangent x. Inner, tangent x times secant x, which is plus tangent x secant x. And last terms, tangent x times negative tangent x is negative tangent squared x. All divided by, I'm going to leave my denominator alone, so I'm going to get the sine of x times secant x minus tangent x. I do not want to distribute this sin x into the parentheses because I need this binomial in my answer. So now looking at my numerator, will I land up at the difference of two squares? Well, I have negative secant x tangent x and positive tangent x secant x. Remember, multiplication is commutative, so it doesn't matter whether I have the secant x first or second. These two are going to add up to 0. And so I'm going to get secant squared x minus tangent squared x, all divided by my denominator of sine x times the secant of x minus the tangent of x. Looking at the numerator, you should think Pythagorean identity. And here's the Pythagorean identity that relates the tangent function to the secant function. And can we manipulate that to get this numerator? Yes, if I subtract tangent squared x from both sides, I get 1 equals secant squared x minus tangent squared x. So this whole numerator just turns into a 1. So I'm going to get 1 over my same denominator of sine x times secant x minus tangent x. Looking at where we want to go, we're almost done. So I can write this as 1 over sine x times 1 over secant x minus tangent x. And what's 1 over sine x? That's cosecant x, and I'm going to write it as a fraction by dividing it by 1, multiplied by 1 over secant x minus tangent x. And last step, multiplying fractions, cosecant x times 1 is cosecant x, all divided by 1 times my binomial. So I'm just going to get secant x minus tangent x. And is this my right-hand side? Yes. So I have shown that the left-hand side equals the right-hand side. So I have verified my identity.